Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right. Good afternoon, everyone. We're delighted to have Van Vu, who was a postdoc here a long time ago, and we're happy for that for many reasons. Particularly when we want to hire a postdoc, we tell them, well, look how people here end up. It's all because of being here. Anyway, and Van is now talking about also one of favorite subject for many of us, roots of random polynomials. Please.
Thank you very much. So it's the ongoing work with Terence Thao and Hoi Nguyen at Ohio State and my student Oanh Nguyen at Yale. So let me just go right into the heart of the matter. So I will start, well, it will be, there will be many other things in it, but let us start with the simplest questions that we want to determine the number of real roots of a polynomial. I will, of course, in the talk there will be things about the complex root as well, but just start like this. We have a polynomial with real coefficient, and okay, that's like an Asian question. We want to know this. And there are a lot of things. For instance, in high school, many of us learned the Descartes rule of psi, it's like 400 years ago, that if you look at the number of psi changes in the coefficients, right, so how many times it switched from negative to positive or vice versa, then that is an upper bound on the number of positive roots. And you can use a similar trick to about the number of negative roots as well. Okay, so for this audience, we will now we talk about the general case when we have a random polynomial. It was random, well, by which we understand that the coefficients are somewhat chosen randomly by some law. And it was first looked at by Waring in the 18th century, that he proved something like this, that the probability of all roots are complex divided by the probability that there's that's the two cases bounded by 2. Now, of course, in this setting, in the old time, it turned out that Sylvester also looked at it later. It's appeared in the book of Todd Hunter. It's, in 100 years ago, it's one of the first textbooks in probability. Now, but of course, in those time, probability or distribution were not determined rigorously, so you can change this number 2 to any other constant if you choose the right distribution for coefficients. So, yeah, but just for the sake of history, that I mentioned that. Okay, so the model we will talk about in the modern language is that we look at this random polynomial when the coefficient Ci are IID is the copies of some real random variable C, and we denote by n, capital N, the number of real roots of this. So this is sometimes referred to as a cut polynomial. Of course, there are other models which, if I have time, I will mention later when the things are not necessarily IID. But let's stay with this for why. So the first result in this direction was obtained by Bloch and Poya in 1932 when they look at the model when the coefficients are uniform 0 plus minus 1. And then they proved that with probability tending to 1, the number of real root is bounded by square root n. Now, which is much better than the root of psi. If you see that we put plus minus 1 there, then the number of psi changes would be linear in n, but they managed to prove square root n by the following idea that you multiply the polynomial with some function which is always positive, and by that you can change the number of psi changing. So it's a very nice combinatorial idea. And it works for other distribution as well. If you have plus minus 1, it works the same way. You don't need the 0 there. And that is block has no picture that I can find. Unfortunately, I think he spent most of his time in the hospital and communicated by mail. And whenever he wrote a mail, he dated April 1st, no matter when he wrote it. So the research picked up with the famous work of Littlewood and Offord as a leading analyst in England in the 1940s. So so it was mentioned as the founding work of Oxford that make him famous. And so in the series of 3 papers in 38 to 43, they show that if you take C to be Bernoulli, so it's plus minus 1, then the number of green root with high probability is bounded between almost log n and log square root n. And they say that the same proof holds for other distributions like Gaussian and uniform. And that's very easy to check to be the case. So in most papers, they focus on the plus minus 1 case. And it was it was sort of surprising for the math community at that time as people guessed that the number of green root is more than log, but this number is really small to what one may expect. So during the same time, there's another important work by Katz. He actually observed a general formula for the expectation of the number of green roots. So he can write down an explicit formula for this. One drawback of this is that it's only easy to evaluate in the Gaussian case, although you can write it formally for any cases, even plus minus 1, but only in the Gaussian case it's sort of easy to evaluate. And it turns out that the expectation is asymptotically 2 over pi log n. Actually, Katz was very enthusiastic when he wrote his first paper and proved this for Gaussian, and he thinks that it should be the same for all other random variables which have say mean 0 and variance 1. And about 5 years, 6 years later, he wrote another paper and saying that, okay, I'm a little bit wrong. I can only do this for uniform, but maybe the result is general. And then there are Stevens. He can show this for smooth random variables. Somehow they managed to evaluate Katz's formula. Now, if we go to the plus minus 1 case, it took a while from Katz's paper. It's the quite a famous work of Erdos and Offord in 56 when they proved again the number is asymptotically 2 over pi log n with the arrow term is like log n to the 2/3. And actually, this proof is quite fascinating. It's do the following, and it's very hard to imagine that why it works. So what they do is they pick a bunch of points, say k point on the real line. Let me just prove the lower bound. Say k is roughly 2 over pi log n. And they look at the value of the curve of Pn at this point, right? So the function at this point, and they say that with decent probability, say probably quite close to 1, the value of the function will change from one point to the other. The size of the value of the function. Yeah. So if you pick these 2 points close to each other, and they manage to show that this is negative, this positive, this positive is negative, and so on. Say, yeah, the nice thing is that they pick this point in advance. They are fixed point, and then they say that with high probability, most of the consecutive pair will have size changes. And then you have the lower bound for the number of roots.
It works because of the repulsion, so they're not going to get multiple zeros in one.
Yeah, of course, you have to make some arrow term somewhere.
But this gives you the lower bound up to the constant.
Yeah, the lower. No, it's give you the lower bound with the right constant.
Yeah.
And then they have to do some other thing to do the upper bound.
So it's saying that they're really very rigid.
Yeah, it is. And then later on, Ibragimov and Maslova generalized the proof of Erdos-Offord and for other random variable with mean 0 and variance 1 and get the asymptotic formula. And if you go into the proof, it's even more complicated than Erdos-Offord and optimize everything, probably you will get the error term of order square root log n for the expectation. Now, on the other hand, from the Katz formula, there's something interesting from there that you can evaluate things very exactly. I think Katz formula in the Gaussian case gives something like this. The density function is equal 1 over pi. It's totally explicit square root of sum over O pair km m minus k square x to the 2m plus 2k minus 2. It is totally explicit function. And if you integrate this function from minus infinity to infinity, you will get exactly 2 over pi log n. And the next term is it's not linear over log n, but the explicit constant, which is asymptotically 0.625. And the next arrow term is actually order 1 over n. And there are people, I think in paper of Willis, even earlier than Elderman and Goslan, they even work out all the Taylor expansion of this. So next term is some constant time over n, and the next one is some other constant over n squared and so on. It can be computed very explicit. Right. Yeah. I want to describe a little bit the argument of Elderman and Goslan, not for the explicit computation, but how you get the 2 over pi out of this for this formula, because you can ask that, well, why the pi has anything to do here? And it's sort of nice argument and work in quite a general case, not only this case. So what they do is the following. If the C are Gaussian, this Gaussian random variable, then you normalize it, you will get the normalize the coordinate vector, normalize the coefficient vector, you get the unit vector on the sphere, unit sphere. Now you look at the moment curve with coordinates 1x and up to x to the n, right? And then the value of the polynomial is actually the inner product of this point on the moment curve with this vector, right? And then this inner product is 0, namely that you have a root at x if and only if this vector is orthogonal to this vector, right? So the number of ring roots is the number of intersection, this should be the intersection, of the projection of this curve onto the sphere and a random great circle, right? That's just geometric argument. So it looks like this. Right, so you have some curve here, which is exact. It is explicit curve. It's the projection of the moment curve onto the sphere, and now you look at the great circle or random great circle and see that how many points intersect, right? And now if you look at this curve, now this curve is complicated, but let's look at a very simple case. When you have a simplest curve, which is another great circle, then you have exactly 2 intersections. Right? Now you take a small piece of this, then you will have 2 times the length of this in expectation. Right? And then you just break this curve into small pieces. So what you get is just the 2 over pi times the length of the curve, and you can compute the curve by this formula. Okay, so now the result I want to present now is the following, that we can prove that for any random variable with mean 0 and variance 1, and say bounded 2 plus epsilon moment, the expectation is 2 over pi plus a constant. Not a constant, plus some amount at big O of 1. So and this big O is, I think, have to depend on the random variable. So it may not be the same constant everywhere. Well, we don't know it is a constant or not. It's just about it.
It's not just a function of epsilon. I mean, on your moment bounds, it's something can be more than the moment bounds.
No, it can depend on epsilon too. So it depends on C. Yeah, this depends on C. And epsilon is the information of C.
But it only depends on your bound on the 2 plus epsilon moment.
Yeah. It depends on epsilon. It doesn't depend on how small that is or how big that is.
SKL, I don't know.
Okay, so yeah, but yeah, and there is still a few questions related to this result. But the main thing is I like to use it as a bait, actually, to present something more significant behind this. The proof is actually more interesting than the result itself, although this is already surprising that you can get to this preciseness. Okay.
I think what James was asking was if for a fixed epsilon and a fixed bound on 2 plus epsilon moment, but various different variables psi, does your error term change?
I see. Probably not. But I don't. Yeah, I cannot do it because. Yeah. So let me tell you the ideas behind the proof, and which actually based on quite a general technique. Okay. So first of all, this thing is standard for people doing random functions, but let me go over it anyway. So if we start with a polynomial like this, right? And if we look at another polynomial which is Qn, defined like this, then we just reverse the order of the coefficient. And it goes from x to 1 over x, so that maps the spectrum from 0, 1 to 1, infinity. So that means that we can restrict ourselves to the number of ring roots in 0, 1. And if we know the number of ring roots here, we multiply a factor of 4, we get everywhere. So from 0, 1 is the same as from 0, 1 to infinity, and the other side of the spectrum is by symmetry. Okay, so first we start with a small fact, and this is where the big O comes from. That if you fix any small delta, say delta is the 1 over 1,000, then with high probability the number of ring root is bounded as a function of delta. This is known from the Littlewood-Offord paper. Well, they didn't state this, but it's inside the arguments. So the spectrum we look at is from 0 to 1. And actually, if I go to even 0.999, here I have only, say, 1,000 root here that I say is a big O. So the ballpark of the spectrum is very close to 1.
Well, then it seems like this transformation was not very good.
It is good.
Because now you put all the roots near 1. Before they were spread out.
No, they never spread out.
It's just symmetry. No, I know. I'm just saying that, like, you're saying all the roots are here.
Yes.
So it seems
All
harder
of
to
that
study
there.
them if you did the transformation the other way.
No.
No, they are there. They are no way
They were
else.
close to 1. They were close to 1 the whole time.
Yes.
Okay, good.
No, I mean, this is a geometric series. Yeah, you think of this guy, Cn as the plus minus 1, right? It will be dominated by one term. It is far from 1.
Is that 1 is a fixed point, the 1 verse?
Okay, so the real part of the proof is we say look at the bulk of the spectrum, and what we prove there is a sort of a universality result, namely that the expectation of the number of ring root doesn't really depend on the choice of the atom variable. So if you replace this C, say from plus minus 1 to Gaussian, then we lose only a small error which go to 0 with delta. Okay. So what I say that, yeah, so this part, actually the number of real roots in the expectation are exactly more or less the same. And then we just make the error term in this. And if you have a different approach to estimate the error term here precisely, then we have a precise bound. Because for Gaussian, everything can be computed very exact. So it's the nice thing is that in the bowl you don't see the influence of the distribution of C error. So every C behaves the same. And on the other hand, we cannot say the same thing for the edge, right, in this interval, because if we take from the interval from 0 to half, we know that the plus minus 1 guy don't have any root. So if you take a random polynomial with plus minus 1 coefficient, every root should have absolute value larger than half. On the other hand, the Gaussian can have root which is less than half. So they are not supposed to behave the same way at the edge. That's why I think that the constant error term could be different from time to time. Okay, so let me go over the main ideas of this. It's actually the proof about some more general universality phenomenon, not only the expectation, but other things as well. So the step 1 in this work is that we prove the universality whole, but for small delta, which is not no longer 1 over 1,000 or 1 over million, but say a small power of n, small negative power of n. So we go even. So we go even to here. It's like 1 minus n to the minus 1,000. And then we prove that that is actually where 80% of the work is. And then we extend this, use a different trick to extend the first result to O small delta. So now let me, because in order to prove this universality, I need to understand the distribution of all roots, not only the real one. And here's a few experiments, some picture which I copied from John Bayes' webpage. If you look at the set of all roots, so complex and real together, there will be n of them, of course. It is well known that in limiting distribution, they go to the unit circle. So it is sort of the picture. I don't know. He make a lot of experiments with high degree polynomial and get this. So there's some weird thing you see here. There's some hole you see near the point 1 and minus 1. So this 1 and minus 1. And there's a fractal of the boundary that I don't know if anyone understands it yet. And there's also some black hole on the circle. And this convergence was proved a long time ago, that we know that it's converged to this by these people. Now let me zoom in the reanalysis when we really care about. So we see a bunch of roots on the reanalysis, but we also see something very nice or something very remarkable here. That's some repulsion between the real roots and the complex. So when you have the real roots, actually we see some hole there that the complex root do not get in.
Sorry, was this for Gaussian?
No, you can do it for any. They give you the same picture. And actually we prove that they will give the same picture.
Not at the level of the same fractal features.
Actually, it's a correlation is a level of 1 over n. It's the right level. It's a universality at the local. So that's what I just mentioned to you all, that we look at the local limit now. So so we have this picture. So we have a huge circle. And now we look at just a small region, right? So near this circle, we expect to see n roots. And now we look at some region D, which is really small. When we expect, in expectation, we see, say, 1 root, right? So that's what I just, okay. And we are going to prove that if in the Gaussian case, we expect to see in D 1 root, then if we replace Gaussian by, say, Bernoulli, we will have more or less the same expectation. And this is going to be true not only for the first correlation function, it's true for any fixed correlation function. But I will not mention that. But what is the point? If now this takes care of the all kind of root, real and complex alike. But if you go to the, let D to be close to the real line, then we know that then by repulsion, if we have a real root there, there's no complex root. So actually, if in this guy we expect to see 1 real root to the Gaussian case, we also expect to see 1 real root in the other case as well, because there's just no complex root by repulsion. Well, we have to prove that there's a repulsion, the same repulsion in the Gaussian case and the plus minus 1 case. So that's also part of the universality. But, yeah. So basically, the thing we really prove with theory is that we prove local universality for all correlation function. That gives you the density, the two-point repulsion, and so on and so forth. That will take care of step 1 and 2. I am not going to define correlation function because it's sort of technical, but I will be glad to discuss more later. Okay, so there's some technical requirement here. That's why we need this condition is that we have to be close to 1, namely that we need the center of D must be reasonable to the unit circle. Yeah. So it cannot be like of distance 1 over 1,000 from 1. It has to be of negative polynomial distance. Okay, so the idea behind this, let me give you the outline through a very simple example, and then we will go to the key observation or the key new idea. So let me introduce this Lindenberg switching idea, which is very useful for proving limiting distribution or universality of the limiting distribution. So the way I understand universality is something like this. You heard the word a few times, but let me define what I think about. So let me have a black box here, and then there's a sequence of inputs, say C1 up to Cn. They are IIDs, random variable, and the black box gives you some function. Right. And this guy has some limiting distribution. Now there's some other sequence, C1 prime of Cn prime coming in, and you have another sequence coming out. Right. And by universality, I mean that if we cannot differentiate the C1 and C1 prime by looking at the output, they would have the same limiting distribution. Right? And one case we know very well is a case when you put in the side the black box, you just take the sum of the CI, normalized by square root n, which gives you the central limit theorem, right? So no matter what random variable with mean 0 and vary once you take the sum and normalize it by square root n, you get the same limiting distribution. Let me prove it here for you by, well, there are several proofs for central limit theorem, but the Lindenberg ones is what we try to imitate later. So it goes like this. Yeah, so we have to care about the limiting distribution of this guy x, which is just a sum. And if we want to control the distribution of this, is more or less enough to control the distribution of the expectation of a test function on x. Say, we can take a test function to be the threshold function like this. Okay, so now in order to consider the x prime, we will do the following, or remember this, the following trick, that is switch C to C prime or C tilde one at a time. So sorry, this guy should be C as well. Right? So first you switch the first one to C tilde. In the second step you switch the second one and so on. So after n step you will get from x to x tilde. Right? And we just try bound this thing by triangle inequality. And one at a time we see how much is the effect in one switching. And if in one switching we condition on everything except the pair that we are switching, then you look at the difference between the two guys, and you can use Taylor expansion here. So you condition on everything else, which give you this xi bar. The first.
Xi bar is not what you wrote, right?
Yeah, I realize, right. Yeah, right. So xi bar is what we get after we subtract, which we need to subtract. Yes, yeah, you are right. Yeah, but yeah, with the right definition of xi bar, then by Taylor expansion you have this. But now if we take the expectation and we know that Ci and Ci bar have the same mean and the same variance, the first two terms disappear. So we will have the third term, which quite magically have the n to the 3 of what? Okay, it have n 3/2 here, and that will kill off the effect of summing n terms. Right? So you will have an arrow term which go to 0, and you can even have a arrow term which is negative power of n. Okay, so that's the main idea behind the linear-based switching. Now, of course, in order to do this, we cannot take f to be the threshold function. We have to smoothen it to take the derivative. And the method works very well for explicit variable x. So if you have the way to write down x as some explicit function in the C, for instance, if not the linear form, but higher polynomial in C, then for instance, there's a work of Mosel et al. That deal with such a case. Have application in computer science too. Okay, so but what we care about here is some function which is fairly implicit, right? Because what we care is this function x, which is the number of root in a region D. So some region D is given near the circle. Now, sure, this is a function in terms of the atom variable C1 up to Cn, but it is not an explicit function like the sum or the polynomial or any way you cannot write it down in any way. That's in order to. And so here's the idea, actually, which I really like. I took it as a while to find it, but once you find it, it works quite simply, in a simple way, that you convert the conversion from implicit to explicit. So what you do is that you look at the root of the polynomial and let f be the function you care about. So it is the indicator of this region. Right? So the number of root we care about is just the sum of the indicator. Right? So the indicator will give us 1 if there's a root and 0 otherwise. No, of course you have to smooth this function a little bit to take derivative. And the key is that there's this green formula that say that if you have a nice function f, then f can be no, it's the same green in calculus. F can be f0 can be written in this way, right? So this is something that actually in calculus we learned. But now we just plug it in and shift everything, right? So fzi should be log of z minus zi times the Laplacian. And when we sum up the right-hand side, then basically we sum up the log. Namely, we take the log of the product but the product of z minus zi are the root of the variable, of the polynomial. So it actually it is the polynomial itself, normalized by the first coefficient, say. So this thing we really care about, the number of root, is now an explicit function. It's completely explicit. It's just an interval. Okay, so that's the first part of the conversion. The second part is that now, although we have this integration, we can prove it, we can estimate it by sampling. We can well, if we have an integration, we can take m random point inside the region and take the mean. That in principle have to give us a good approximation of this number. Now, okay, so now after we take this sample point, y1 up to yn, and fix them, then now this function x, which count the number of roots, is an explicit function of those gy1 up to gym. And now you can use the Riemann here to prove the universality of this vector. Very the same way. Yes. Well, it's 30 pages. It could be problem.
Everything looks very natural except the last step. So I'm surprised that doesn't sampling here just add error? Can't you just do the same method but do the replacement on the integral instead of on the sampling?
What?
Why are you sampling? I mean,
Because I need this guy to be fixed. And here m will be a small power of n.
Yeah, but can't you just do directly the replacement method on the integral and show that the integral doesn't change much?
I don't know how to do that. Maybe there's a better way to do that. Yeah, and if there is a simpler way to do that, that would be nice. But yes, so that's the idea. Okay, and so in order to prove that the sampling is give you the right thing, then we have to bound the variance and so on. And so that's this part is it is the technical tool we need to bound the variance here. That's because we want the sample to make the right estimate, so we have to say that, okay, the variance of this guy is small, and basically it's boiled down to say that the log of the function is not too large for most point z, and that part you have to deal with. So why this thing is not entirely trivial? We want the log is not to be large. Now, the value of Pn itself is very easy to bound from above, right? Because it's sum of n term and they are random variable with bounded variance. So from above it is not too bad, but one thing is which is less trivial, that you need to bound it from below, that it is not too small. And that is not entirely trivial, that how you use that, because it can be sometimes small. Yeah, if you look at the value of some special value of z, then the value of the polynomial evaluated as z can be really 0. For instance, if you look at z to be, say, the cubic root of unity, right? And then now you look at this guy. W and W square, W third. So this guy will be 1, and now you up W to the fourth will be W and so on, right? So actually, if you have to sum this guy up, then they are periodic, right? So then you can rewrite your polynomial like this, right? Because they are periodic with period k. Yeah, but now this guy can be 0 with some decent probability. Yeah, so if we split out things, it will be right. It will be write it as a polynomial in W. So the free coefficient is this, and it's the sum of n over k terms. So next coefficient also is the sum of n over k term. And each of these guys have a decent chance to be 0. They have a chance of square root, 1 over square root n chance to be 0. So the probability equals 0 is not small. It can be like n to the minus k over 2. So it can be n to the minus 1/2 or n to the minus 3/2, so on. And this cannot be ignored totally. And so the lemma we really have to prove is that actually this k root of unity are the only troublesome point. If we can avoid, get a little bit far away from the k root of unity, then the probability that your our polynomial is small is very small. And it is something that I built, or we built in the last few years, so-called the theory of inverse Littlewood-Offord, which deal with the following question. This can be seen as an anti-concentration result. That the main question is that we have a linear form like this, and we want to know that how much mass can it pick up at 0 or any point for that reason. Right, so the classical result of Littlewood and Offord say that if the AI are non-zero, then this probability equals 0, cannot be more than 1 over square root n. Now let's see that if we are not satisfied with 1 over square root n, we ask that what happens if I want the probability to be as small as 1 over n cubed. What can you do then? Okay, so now we look for reason that make this concentration probability to be large. Say, and the trivial one is the following. Let's imagine that all the AI are integer, and they are integer in the small interval of some length n to the 3, say. Right? Then by the central limit theorem, we know that with a fair chance, say at least 0.9, s should be in the square root n blow up of this interval. Right? So the probability that s equals 0 by pigeonhole principle is the reciprocal of the length of the interval. You have a short interval and the mass is in there, so there would be the point when you pick up more mass and just the reciprocal of the length, and you take the length to be polynomial, then the probability can be polynomially large. Okay. You can generalize this to higher dimension if you take AI to be point in a Minkowski sum of the arithmetic progression, and with volume n to the c, then you will have similar bound, which is right here. So what is enough to keep it? This is the first case in mind. What we really prove in this direction is that if we assume the inverse, so namely that we assume this bound in advance, that the probability, if have a mass point with mass at least this much, then actually most of the coefficient AI has to be in an arithmetic progression of the right length. And that's the okay. But if we look at go back to the problem that we had before, is that we have the sum of the AI, sum of the CI, W to the I, right? And we care about this probability 0, say that this probability is large. Right? This is only the toy case, because what we really care about is that this probability is small, not only 0, but let me take this toy case. Then my AI will be this. Right? So if I say that this probability is large, that means my AI have to be in a short arithmetic progression. And AI here is equal to z to the I, say. And that will imply that the z should be an algebraic number with low degree. And this somehow give you a, well, now you have a feeling that why say the cubic root of unity will be the only bad example. So that this comes from the fact that you really work with algebraic dynamic of low degree, and somehow you can go to that from here. Okay, so that part plus the universality project sort of take care of the first part of the argument when we can have universality from 1 to 1 minus some polynomial function of n. And by the way, the reason that this has a long history, that's why we come to this idea because it started a long time ago when we started to work on universality of random matrices. So the key problem there is to prove universality of the correlation function. And there's two groups working on that, Terry and I, and then Erdos and Yale and their co-author. And we work a lot on random and Hermitian matrices, right? So it's either complex or real and symmetric. Complex and Hermitian and real and symmetric. So in this case, we know that the eigenvalues are in number, and the problem here was solved quite successfully for the complex case and partially solved for the real case. So we have good result there. On the other hand, another model popular in random matrix theory, just take IID with no symmetry. So if you have n square random bit in the matrices, now the eigenvalue will not be real. They are mostly complex, and well, the correlation function question makes sense as the same way as before. And the original, the first methods that Terry and I, and also the method that Yao and Erdos developed, it doesn't work for this case at all, because it's rely very much on the fact that Hermitian matrices are not do not react to small perturbation. On the other hand, we know that a small perturbation to a non-Hermitian matrices can change the spectrum quite a bit. So we have to find a new method to deal with this, and then actually this method was sort of invented to deal with the IID case. And then we realized that it worked for polynomial as well. So and you can also use it for the original setting. Of course, it doesn't lead to any new result, but it sort of give a common approach to deal with random processes. Right, so now the last part of the puzzle is that we have to go from this, the universality very close to 1 to universality not so close to 1. Right? So, yeah, so we know that we get result from here for Pn, but our goal is that we want to go to 1 minus delta for some small delta. So we need to extend that range. And this boils down to understanding something from numerical analysis. This is another question which is interesting by its own, namely that how often does a random polynomial have a double root, or even near double root in some sense. For instance, if you want to run like the most popular method to compute roots is the Newton algorithm, then the running time is very crucially depend on the existence of double roots. So if so you don't have double root, then the running time improve exponentially. Okay, so what we can show is that we can have, well, this is actually not zero. We can have, if you look at the interval from 1 minus delta to 1 minus, say, like log n square over n, then you are not going to have a double root, actually not even going to have a near double root, namely that the root and the derivative is not 0 but very small. Then we don't even have this case. Yeah, it's not 0 here, it's like 0.99. And so let me tell you why this is helping our course of extending this universality. The thing is that I try to cheat here a little bit. Yeah, so if you so given Pn, I can go from 1 to 1 minus n to the minus delta. And now we have to go from here to a next one, say 1 minus, from L to the minus delta. Right? And now I can look at for some L, which is some small power of n. Instead of Pn, I look at Pm. So it's a polynomial of degree m. And I'm saying that in this interval, actually Pn and Pm, the roots in this interval are more or less the same. Because if you look at Pm is like this, C to the m, and Pn is exactly this, and now you add term like this in there. Right?
Can you say what is the assumption, what's the conclusion? I mean, this statement up there, the statement up there, because it's not true if you have double roots.
Yeah, of course, that's why. That's why we need to prove the non-existence of double roots. Yes.
Right. Okay. So
Yeah, that's the beginning. That's the beginning of how I try to extend it, right? If I can have something like this, then actually I can replace Pn to Pm by some smaller m. And then I say that instead of n to the minus delta, I can take m to the minus delta and I iterate that. Now this only works if f and g in itself, they don't have double root. And that is exactly the length. So, yeah, and so if they don't have double root, then the number of roots differ by very little. I don't make any mistake when I do this trick. Yeah, so that's why we need this near double root. Not only double root, but near double root. Yeah, so the roots are separated, and the root of fi and the root of g are close to each other, so they have the same number of roots. Okay, so that is about the main idea. Yeah, so there is a bunch of questions that
You didn't say how you argue about the non-existence of double roots.
Yeah, so that's a separate thing. That's another paper. Right. Yeah, so we do this and iterate. Yeah, so that's basically the main ideas. Each of it. And here's some other things that we can do with this technique that we mentioned. Right? So yeah, so we can prove a correlation function of this. Yeah, we can look at other model of random polynomials when the variants of the CI are different. So there are classes which are popular in the literature, like we can look at polynomial of this type. It's called the Weil polynomial, and polynomial of this type, maybe square root, I don't remember. It's called the binomial polynomial. And so Yuval had a book about the case when we don't look at polynomial but look at the infinite extension, the series. There's a lot of interesting properties of this series, random series. Anyway, we can extend to random series too. And as I mentioned, random polynomial with dependent coefficients can also be considered. The only case we consider here was the characteristic function of random matrices. So basically, we do this correlation for eigenvalues. Yeah, so there's many other interesting cases that may come to mind. One interesting question that I don't know how to solve is what is the constant in the big O? Right? So we know the very first result I mentioned, which I started with, is that E of n c n equal 2 over pi of n. And now we know the arrow term, which is about it. Well, there are two questions actually. First of all, does it tend to a limit? That's the question I mentioned at lunch last week. We know this for the plus minus 1 case. And of course, it was known for the Gaussian case. Otherwise, we don't know. And even when it tends to the limit, we don't know what the limit is. We have no reasonable bound for this. We know that it's less than 10 to the million, but that's about it. And it is ultimately connected to the existence of double root from, say, 0 to 0.99, the question I mentioned last time. So thank you very much.
Any additional comments, questions?
What are the guess? So it's not going to be the same concept, right?
No.
You have experimental
And I have a
results.
numerical experiment that it shows maybe off by 0.3 or something.
So it's bigger,
Smaller.
smaller. So that's for the Bernoulli.
Yeah. But I don't know it is bounded by a million or not. So right now, if you prove the bound is less than a million, it's already new.
You mean the constant for plus minus
Plus
1?
Yeah,
You
for
know
plus
the
minus 1,
constant.
I don't know it, it is less than a million. I know it is there. But the experiment is like 0.4.
And for other distributions, there's still a problem to show no probability of having a double zero.
That we haven't tried very much. Actually, there are recent development here that for other distributions like the Gauss case, for the Weil polynomial, now we managed to actually prove universality closer to the origin. So you don't need to be polynomially bounded away. Actually, it's enough to be, I think, constantly bounded away. Then that already gives the big O zero arrow term. But the big O is bigger.
On the interval next to the near 1, you have very good control, right?
Yes. There
so
we know
so
very
there the
precise.
arrow is like 1 over n.
Yes.
But then with this delta and all
from
this truncation,
0.
what you get is the arrow term eventually. Okay.
Well, from the what the cheat is from delta. If I fix the delta, I can tell you the arrow term here depending on delta quite nicely. I don't know what delta is. So my delta is 1 over 10 to the million. That's the problem. So the number of root will be the log of that, which is a million, which I just told you. We don't have a good bound on delta. If you have a good bound on delta, there are quite good estimates for the number of root from 0 to 1 minus delta. That's not good.
Right, let's thank Van again.